The purpose of this lab was to observe how resistors and capacitors impact current and voltage measurements throughout a circuit and determine the time constant for an RC circuit. Concepts used in this lab are steady state, which we demonstrated using ammeters in a series circuit, the loop rule for energy conservation, which I demonstrated for a series circuit with 2 resistors, Ohm's law, for which we calculated the actual resistance of circuit elements based on delta V and I measurements, and capacitance, for which we determined the time constant for a simulated RC circuit, and I found it to be 6 seconds based on my experimental data. First, we were asked to consider a series circuit with 2 1.5 volt batteries, 2 different resistors, and 2 ammeters measuring currents I1 and I2. I predicted that I1 and I2 would be equal because they are in series, so along the same path and in steady state. To find what the current should be, I set up the loop rule equation for the whole circuit. Assuming the 2 currents are the same, they should both be equal to 0.0204 amps. I created the circuit and the circuit construction kit virtual lab as shown in the picture and found that my prediction was correct. And then reversing the connections on the ammeter gave the same magnitude of current. Replacing one ammeter with a voltmeter gave a voltmeter reading of 3 volts because each battery provides 1.5 volts, and an ammeter reading of 0 amps because voltmeters have very high resistance, so when placed in series, the current is restricted at later nodes. Next, the voltmeter was taken out of series and replaced with a wire to close the circuit. The potential difference for each segment of the circuit was measured using the voltmeter and recorded in the table shown. The sum of all the readings was 0, which is expected because this means the circuit obeys the loop rule and energy is conserved. The potential difference data was used to plot the potential relative to the negative end of the battery versus position around the circuit. Final observations. The ammeter reading didn't change while taking measurements with the voltmeter because we put it in parallel with the circuit and the resistance on voltmeters is so high that no current is diverted away from the main circuit. And then placing an ammeter in parallel with the 100 ohm resistor changed the other ammeter's readings from 0.02 to 0.06 amps. And this is because ammeters have very low resistance, so more current travels through the new path with lower resistance rather than through the large resistor. Finally, the experimental resistance values for each circuit element were calculated using Ohm's law. Next, I assembled an RC circuit in CCK as shown in the figure, and the following observations were made. When the capacitor was charging, the light was very bright at first and then dropped down dramatically. What's happening is the current in the circuit slowly decreases as charges build up on the capacitor plates. The electric field created by this buildup counteracts the electric field from the conventional current in the wire until equilibrium is reached in the circuit. And then when the capacitor was being discharged, the bulb was initially very bright and dimmed out over a slightly longer period of time. We know that electrons migrate away from the negative plate towards the positive plate through the circuit, and this migration causes both plates to lose all excess charge until the electric field and thus the current reach 0. The amount of time required to charge and discharge each bulb was measured and recorded in the table shown. The data confirm the observation that each capacitor takes slightly longer to discharge than to charge. A circuit containing only a resistor and capacitor was analyzed next in the virtual lab as shown in the picture. We applied the loop rule for energy conservation to this situation. The voltage drop over each element should sum to 0. And then we use what we know to derive an expression that can ultimately be graphed to find the RC value based on our experimental data. RC is the time constant, or the time at which the electric potential has dropped to 1 over E of the initial. The result I got for my RC value was 6 seconds, which agrees with the theoretical RC value, which is resistance times capacitance, and is also 6 seconds. What would happen if I used a real ammeter? Real ammeters have a very low resistance rather than 0 resistance like the simulations. Ideally, real ammeters would have 0 resistance, but this isn't possible. In our circuits, a real ammeter would restrict the magnitude of the current because it acts as a small resistor. And then what if I used a real battery with no resistor? Real batteries have an internal resistance which increases over time as the battery is used. Our ideal model would predict the capacitor to reach full charge instantly with just a battery connected, since there's no resistance. This wouldn't happen in real life because it would take a small amount of time for the current to move across the battery first, as it faces internal resistance. So in conclusion, Current and charge are conserved when a circuit is in steady state. The total electric potential difference along a path in a circuit should sum to zero because energy and electrons cannot be created nor destroyed. Multimeters can be used to collect data about a circuit in simulations and reality. I observed that capacitors in circuits with larger resistors take longer to charge and discharge. And I determined the time constant of our RC circuit to be 6 seconds by deriving an expression from our loop rule equation and solving using experimental data.